Welcome on this presentation on projectively matched frame difference. This is video processing research done in the context of my eDirector 2012 project, research conducted at Athens Information Technology. Camera understanding in sports recordings is very important. In such recordings, cameras change in order to follow the action. They usually pan, tilt and zoom, but sometimes they even move to different locations. Understanding camera motion is very important for two reasons. First of all, it allows us to separate the foreground, and this aids in detecting the body of athletes. Secondly, it allows us to understand the phases the various sports events undergo. Cameras covering sports events mostly pan, tilt and zoom progressively in order to follow the action. The action thus remains centered, while background undergoes projective transformation. Knowledge of this projective transformation between successive frames yields offset and zoom estimates. On the right-hand side, you can see the transformation matrix that is obtained using four usual affine transformations: the translation, the scale change, the shear, and the rotation. Now, if we can assume that the rotation, shear, and projective transformation are negligible, then the transformation matrix has this form. If the change between two consecutive frames is not large, portions of the previous frames can be matched to the current one. We can establish points of interest, key points, in both frames and attempt to match them. Matching is used to derive the projective transformation between the two frames. In this example, you see the two frames of interest and the key points in each of the two that are matched together. To see the effect of actually finding the projective transformation, here you see the frame-by-frame difference where the background and the athlete change a lot. On the bottom right, you can see the frame by projected transformed frame difference, where you see that the background in the two frames is matched due to estimating the transformation between the two. Now, what remains different is the athlete body itself. The corners are used as feature points because they are uniquely identifiable in images. The Harris corner detector returns a metric whose magnitude represents the strength of a corner. This gives us information on how pronounced the corner is compared to neighboring pixels. This metric is globally thresholded, and the distinct peaks are identified. We have a few hundred key points originally returned by the Harris corner detector. We can reduce this number of key points by eliminating weaker corner points in the vicinity of stronger ones. The radius of the neighborhood where the stronger point survives determines the number of key points to be matched. We are interested mostly only on the peripheral key points and those not belonging to known targets. The wanted key points are on the track or field, the advertisement board, the audience area and the stadium itself. We need to avoid key points on the bodies of the competing athletes themselves. Key point matching is done by block matching. We utilize a square extending 8 pixels in every direction around the corner points. This unfortunately only accounts for shifts, but on the other hand, the large frame rate guarantees that there will be only significant shift between the two neighboring frames. In the example, you can see the corner points to be matched in one frame as red discs, the position of these corner points in the next frame as circles, and also as red discs the actual moved corner points that are matched to the previous frame. The matched key points with small mean square error are selected. And these selected key points are used to estimate the projective transformation between the two frames. This is a demonstration of a long jump attempt. You can see in the top left the video frames. In the top right you can see the projectively matched key points and the motion outliers. In the bottom right you can see the projectively matched frame difference, which does not have the background but only the athlete bodies. The evidence of the background is shown in the bottom left, where you see camera motion results in lots of background. This algorithm does have problems when you have foreground objects occupying most of the frame. But in cases like this, where background objects are indeed uncovered, we can find enough key points there in order to perform the projectively matched frame difference. Notice as the athlete starts running down the aisle, the background in the bottom left is very evident. This background does not exist in the projectively matched difference. Here's another demonstration on 5,000 meters walk. You can again see the background being evident in the frame difference image and not being evident in the projectively matched frame difference. We can detect the bodies of the athletes even in very far recording conditions, like in this frame. Another demonstration uses discus, and you can see the attempt here. Again, background is eliminated. You can detect the discus itself in the projectively matched frame difference. Again, the discus is very evident. This is another example using pole vault. No background is evident in the bottom right image, and the athlete carrying the pole is evident. The camera motion also results in camera parameters, the tilt, the elevation and the zoom. These are very important in understanding the phases the various sports events undergo. This is an example with a profile camera in long jump attempt. At the beginning, the athlete is preparing and the camera does not move at all. When the athlete starts running down the aisle, then you see the tilt and the elevation to change, and you also see that the zoom factor of the camera changes. It zooms out in order to keep the athlete body at approximately the same size. When the athlete lands on the sand, then the camera stops moving and you can understand that the attempt has finished. This is another example with the same long jump attempt, only recorded from a frontal camera. Again, there is no motion while the athlete is preparing, but when the athlete starts running down the aisle, you have the zoom decreasing and the tilt and elevation of the cameras increasing. The elevation itself abruptly drops and increases the moment the athlete lands on the sand.